Hi, it's me, Mike Yawn, back with a supersized episode of Television. Today we're going to take a look at performance features of the Hazelcast platform. Now in this series we'll do deep dives into many platform features, but it's useful to have a larger context of a broad topic before going deep into specific features. So the purpose of this episode is to provide that context for the features that enable the high levels of performance for which Hazelcast is known. We'll have other overview episodes for some of these other feature sets, as well as deep dive episodes into some of the key features in each category. So let's get started.
Performance tuning is like a game of whack-a-mole. When you find and smack down one performance bottleneck, another one will inevitably pop up to take its place. But unlike the arcade game, winning this game isn't a matter of reflexes or anticipation. It's about having the right tools. In this episode, we'll take a quick look at the capabilities Hazelcast adds to your toolbox. And rather than just listing them, we'll actually walk through a progression of challenges and solutions. Now, you may not encounter all of these issues, or you might hit them in a different order, but I think the progression is typical and should resonate with many of you. So our progression starts with an application that uses a database and it isn't achieving the required level of performance. The issue is usually going to be the speed of disk I/O. Concurrency within the database might be a factor as well. So the solution is to put an in-memory cache in front of that database. This is going to solve the disk I/O bottleneck. The primary feature of Hazelcast we're using here is our fast data store. By storing data in memory rather than on disk, we get much faster access. The threading architecture of Hazelcast, which we covered in episode 3, gives us thread-safe concurrent access to the cache data, which could improve both throughput and latency. Now, flexible data connection access, such as generic or custom-built map stores, provides read-through, write-through, or write-behind access to the underlying database to ensure that the data we need is in memory when we need it. And if needed, we could also use change data capture to keep our in-memory data in sync with changes being made to the underlying data store. So now we see that we have only a single node of cache being used, and this could limit our ability to keep a reasonably sized working set in memory. Fortunately, since Hazelcast is clustered, we aren't going to be restricted to a single node. So here's the same basic architecture, but with multiple nodes. The main enabling feature here is Hazelcast's clustered architecture, featuring elastic scaling so we can increase or decrease our capacity to meet changes in demand. But we have other ways to manage our memory consumption other than just throwing more hardware at it. We can set eviction policies and time to live values so that we aren't caching data that isn't currently needed. There are also two features in our Enterprise Edition which allow us to increase the amount of usable storage per node. High-density memory moves data off the Java heap, eliminating garbage collection pauses that can wreak havoc on latency, and allowing more of the memory to be used effectively. And tiered storage allows us to spill to disk when we exceed the allocated amount of memory. Now, what's likely to happen at this point is this. We've made all of the data available for fast access, and applications are greedy for data, so they're going to want more of it. And that's going to cause us to exceed our network capacity. We can conserve bandwidth by being smarter about what we send over the network. The biggest impact is seen when we use more efficient serialization options. We'll have an entire episode on this coming up. We can also reduce the data sent by returning only fields we need rather than entire objects by using the projections API or writing SQL queries that select only the columns needed. It's also more efficient to do bulk operations like a put all, sending many entries at once, rather than looping and putting individual entries. And if we don't need return values, Hazelcast 8 has APIs like set instead of put or delete instead of remove, which don't return the previous value. So if you don't need it, don't use up your network bandwidth with unnecessary traffic. These are all nice optimizations, but they may not get us to where we want to be. Let's take a look at something a bit more dramatic. A lot of times we need to do more than just a simple read. We could read, update, and then put the data back. Or perhaps we need to fetch a bunch of data and loop over it doing some computation. If you need to move data across the network to operate on it, it's likely going to be more efficient to instead move the code to where the data lives. Code is small compared to data. Hazelcast has many features that provide distributed compute capabilities. Now, the advantages here are threefold. First, we can save network bandwidth by not needing to move data. Secondly, we can take advantage of partitions to do operations in parallel, using multiple CPUs across multiple members, dramatically reducing latency. And third, we don't have to have locks if we perform mutating operations, again because of the thread-safe nature of partitions. We will, say it along with me, talk more about this in future episodes. Distributed compute is really the key differentiating capability of Hazelcast versus a simple cache. So if you're not taking advantage of this, you're leaving potentially huge performance gains on the table. Now, with all this clever stuff, we've probably reduced network usage quite a bit. So we probably aren't facing a network saturation problem. But if we look at the components of our latency, we probably see that network calls still make up a good part of it. And this is because fetching data across the network is always going to be slower than fetching something from local memory. The most efficient way to use the network is not to use it at all. Near cache allows us to cache data on the client side. This works best when we have a read-intensive usage pattern, and especially if we tend to reread the same items repeatedly. Now, it's not unreasonable that we just spent far more effort on network fixes than we did up front fixing our I/O bottleneck. It turns out that caching is easy, but making distributed systems work is hard. We can now finally turn our attention to the CPU utilization on our member nodes. Depending on how compute intensive our workload is, we may find that we are either overutilizing or underutilizing our CPU capacity. Let's first consider the case where you aren't keeping all your CPU cores busy. This is quite common for caching type workloads. We have a couple of useful features here. A thread per core architecture, which is new in our release 5.4, helps us better match compute resources to workload. We aren't as dependent now on having the right number of partition threads configured. So whether you're deployed on small systems with fewer cores or very large systems with lots of cores, we can better allocate the CPU resources. And this architecture results in fewer context swaps, so more CPU is going towards productive work. Jet pipelines is another way we can distribute work across available CPUs. We'll take your pipeline, which is a declaratively defined workflow, and break it into tasklets, which are then distributed to all nodes and processors. A cooperative multi-threading model schedules these tasklets, ensuring that all CPUs are effectively used when there's work to be done. Now, sometimes if you have a really compute-intensive workload, these techniques will mean that all your CPUs become fully utilized, and now you'll be bottlenecked on CPU capacity. If this is the case, you can configure additional nodes as light members. These are members that don't store data, so they purely contribute additional CPU capacity to help provide a computing boost. Now, that's the end of our walkthrough progression, but it doesn't mean that there won't be further challenges. You might have bottlenecks in your application code or be running into physical limits like that pesky speed of light, and we're probably not going to have a fix for that one. But that doesn't mean that we won't keep looking for ways to squeeze more performance out of the workloads you deploy on Hazelcast. We're running along today, so I'm not going to do a cluster facts recap, and we'll be back soon with another episode. Thanks for tuning in.